Definitions of continuity. Continuity at a number. A function f is continuous at a number x equals c if the limit of f of x, as x approaches c, is equal to f of c. The equation implies three conditions. First, f of c is defined, in other words, x equals c is in the domain of f. The figure on the right illustrates this condition of continuity at a number. Suppose the graph of a function y equals f of x passes through x equals c. F of c is defined because the graph of f touches or intersects x equals c. For emphasis, it may be represented as a solid point at x equals c. If at x equals c there is just one hollow point, and no solid point, an infinite discontinuity, or just no graph of f, then f of c is undefined. Second, the limit of f of x, as x approaches c, exists, in other words, the one-sided limits are equal. Third, the limit of f of x, as x approaches c, is equal to f of c. If these conditions are satisfied, then f is continuous at x equals c. The figure on the right illustrates these conditions of continuity at a number. The two-sided limit of f of x, as x approaches c, exists, and is equal to L, because the one-sided limits approach the same number L. The limit of f of x, as x approaches c, is equal to f of c, because there is no hole on the graph of f at x equals c. Therefore, f is continuous at x equals c. Examples. Determine whether f is continuous at x equals c. Number 1. Is f of c defined? Yes. Does the limit of f of x, as x approaches c, exist? Yes. Because the one-sided limits both approach the same number. Is the limit equal to f of c? Yes. Thus, f is continuous at x equals c. Next figure. Is f of c defined? Yes. Does the limit of f of x, as x approaches c, exist? Yes. Because the one-sided limits both approach the same number. Is the limit equal to f of c? Yes. Thus, f is continuous at x equals c. Next figure. Is f of c defined? No. Does the limit of f of x, as x approaches c, exist? Yes. Is the limit equal to f of c? No. Thus, f is discontinuous at x equals c. Because at least one of the conditions has not been satisfied. Next figure. Is f of c defined? Yes. Does the limit of f of x, as x approaches c, exist? Yes. Is the limit equal to f of c? No. Thus, f is discontinuous at x equals c. Because at least one of the conditions has not been satisfied. Number 2. A. f of x equals negative x. If x is less than 0, and x squared, if x is greater than or equal to 0, with c equals 0. Solution. First, determine if f of c is defined. F is defined on x greater than or equal to 0, which includes x equals 0. Its value is given by f of x equals x squared. F of 0 is equal to 0. The figure illustrates the graph of f of x. The value of f at x equals 0 is defined, and it is equal to 0. It is represented by the solid point. Thus, f of 0 is defined. Second, determine if the limit of f of x, as x approaches c, exists. Compute the right-hand and left-hand limits. The one-sided limits are equal. Please refer to the figure and that the limit of f of x, as x approaches 0, exists, because the one-sided limits are the same. Therefore, the two-sided limit exists, and it is also equal to 0. Third, determine if the limit of f of x, as x approaches c, and f of c are equal. The limit of f of x, as x approaches c, and f of 0 are equal to 0. F of 0 is defined. The limit of f of x, as x approaches 0, exists, and they are equal. Hence, f is continuous at x equals 0. B. f of x equals negative x if x is less than 0, and x squared if x is greater than 0, with c equals 0. Solution. First, determine if f of c is defined. F is defined on x less than 0 and x greater than 0 but not at x equals 0. Consequently, f of 0 is undefined. Because x equals 0 is not in the domain of f. The figure illustrates the graph of f of x. The value of f at x equals 0 is undefined. It is represented by the hollow point. Therefore, f is not continuous at x equals 0. Even if the limit of f of x, as x approaches 0, exists, c f of x equals negative x, if x is less than 0, 1, if x is equal to 0, and x squared, if x is greater than 0, with c equals 0. Solution. First, determine if f of c is defined. F is defined on x less than 0, x equals 0, and x greater than 0. At x equals 0, the value of f is f of 0 is equal to 1. The figure illustrates the graph of f of x. Second, determine if the limit of f of x, as x approaches c, exists. From the example number 2. A. The one-sided limits are equal and are equal to 0. Hence, the two-sided limit exists, and it is equal to 0. Third, determine if the limit of f of x, as x approaches c, and f of c are equal. The limit of f of x, as x approaches 0, is not equal to f of 0. Therefore, f is not continuous at x equals 0. D f of x equals 1 minus x, if x is less than 0, and x squared, if x is greater than or equal to 0, with c equals 0. Solution. First, determine if f of c is defined. F is defined on x less than 0 and x greater than or equal to 0, or equivalently, on all x in the real line. At x equals 0, the value of f is f of 0 is equal to 0. Second, determine if the limit of f of x, as x approaches c, exists. The right-hand limit or the limit from the right of 0 is the limit of x squared, as x approaches 0 from the right, is equal to 0. The left-hand limit or the limit from the left of 0 is The limit of 1 minus x, as x approaches 0 from the left, is equal to 1. The figure illustrates the graph of f of x. The value of f at x equals 0 is defined, and it is equal to 0. It is represented by the solid point. The one-sided limits are not the same. The limit does not exist. Therefore, f is not continuous at x equals 0, even if f of 0 equals 0 is defined. Discontinuity at a point. A function f is discontinuous at x equals c if any one of these is true. First, f of c is undefined. That is, x equals c is not in the domain of f. F of c is undefined if f has a hole at x equals c. In addition, f of c is undefined if f has an infinite discontinuity at x equals c. Second, the limit of f of x, as x approaches c, does not exist. It means that the one-sided limits, as x approaches c, are not equal. Also, it means that the limit, or any one-sided limit, as x approaches c, is an infinity. Third, the limit of f of x, as x approaches c, and f of c are not equal. There are two types of discontinuity. Removable discontinuity. It is a discontinuity that can be removed by redefining the value of f at the point of discontinuity. For example, if f has a whole discontinuity at x equals c, redefining f of c such that it is equal to the limit of f of x, as x approaches c, removes the discontinuity. Non-removable discontinuity. It is a discontinuity that cannot be removed even if the value of f is redefined at the point of discontinuity. Some examples of non-removable discontinuity are infinite discontinuities and jump discontinuities. Redefining the function at a point of discontinuity does not make the function continuous at that point. Example: determine the continuity given the graph of f. Number 1. f of x equals 1 over quantity x squared minus 5. Solution. The graph shows that F has infinite discontinuities, which are non-removable discontinuities, at x equals negative square root of 5 and x equals square root of 5. F is discontinuous at x equals negative square root of 5 and x equals square root of 5. Number 2. F of x equals x cubed plus x squared minus 9x minus 9 all over quantity x plus 1. Solution. The graph shows that F has a hole at x equals negative 1, which is a removable discontinuity. It means that F is undefined at x equals negative 1. F is discontinuous at x equals negative 1. Number 3. F of x equals x plus 1 all over quantity x cubed plus x squared minus 9x minus 9. Solution. The graph shows that F has a hole, a removable discontinuity, at x equals negative 1. Moreover, F has infinite discontinuities, non-removable discontinuities, at x equals negative 3 and x equals 3. F is discontinuous at x equals negative 3, x equals negative 1, and x equals 3. Number 4. F of x equals square root of x, if x is greater than or equal to 1, and 1 minus x, if x is less than 1. Solution. The graph shows that F has a jump, i.e., a non-removable discontinuity, at x equals 1 where the formula of F changes. F is discontinuous at x equals 1. Even though F of 1 is defined. Continuity on an open interval. A function f is continuous on the open interval a, b. If it is continuous at each number in the inequality x greater than a and x less than b. It means that the equation for continuity at x equals c holds for each number in the interval a, b. The figure on the right illustrates the concept of continuity at an open interval. The graph of y equals f of x is continuous on the open interval a, b. If f has no discontinuity, hole, jump, or gap at any number between x equals a and x equals b. The holes on the graph of f at x equals a and x equals b indicate that they are excluded from the open interval a, b. That is, the limit of f of x, as x approaches c. For any number c in the open interval a, b, can be calculated by direct substitution of x equals c into f. Direct substitution is allowed between x equals a and x equals b. Continuous everywhere. If f is continuous on the entire real line, it is continuous everywhere. Examples of continuous everywhere functions. Number 1. Polynomial functions. Number 2. Trigonometric functions, sine of x and cosine of x. The graph of y equals f of x is continuous everywhere if f is defined and has no discontinuity, hole, jump, or gap, on the real line. Number 3. Exponential functions. Number 4. Hyperbolic functions. Hyperbolic sine. Hyperbolic cosine. Hyperbolic tangent. Hyperbolic secant. Number 5. Inverse hyperbolic function. Inverse hyperbolic sine. Meanwhile, other transcendental functions are not continuous everywhere. Example: determine the continuity of the following functions. Number 1. f of x equals 6x plus sine of x. Solution: the limit of f of x, as x approaches c, by direct substitution is calculated as follows. Because the limit exists for any c in the real line, f is continuous everywhere. 2. f of x equals 3 over x minus the cosine of x. Solution: the limit of f of x, as x approaches c, by direct substitution is calculated as follows. C equals 0 is not allowed because a number divided by 0 is undefined. Hence, the limit of f of x, as x approaches 0, does not exist. That is, f is discontinuous at x equals 0. 3. F of x equals 1 over quantity x minus 4 quantity squared times quantity x plus 3. Solution. Calculate the limit at any x equals c by direct substitution. C equals 4 and C equals -3 are not allowed because the denominator becomes 0. Hence, the limit of f of x, as x approaches 4, or, as x approaches -3, does not exist. That is, f is discontinuous at x equals 4 and x equals -3. Continuity on a closed interval. A function f is continuous on the closed interval a, b. If it is continuous at each number in the inequality x greater than or equal to a, and x less than or equal to b. The following conditions must be satisfied. First, f is continuous on the open interval a, b, that is, the limit of f of x, as x approaches c, equals f of c at every c in a, b. The figure on the right illustrates this condition of continuity on a closed interval. F has no discontinuity at any number between x equals a and x equals b. Second, F has one-sided continuity at the endpoints a, continuous from the right at a. The limit of f of x, as x approaches a, from the right, equals f of a. In the figure, continuity at a means f of a, the solid point at x equals a, coincides with the limit as x approaches a. From the right, b, continuous from the left at b. The limit of f of x, as x approaches b from the left, equals f of b. In the figure, continuity at b means f of b, solid point at x equals b, coincides with the limit as x approaches b from the left. F has no discontinuity at the endpoints x equals a and x equals b. That is, the limit of f of x, as x approaches c, for any c in the closed interval a, b, can be calculated by direct substitution of x equals c into f. F should have no discontinuity, such as a hole, a jump, or a gap, at any number from x equals a to x equals b. Example: determine the continuity of the following functions. Number 1. F of x equals the square root of quantity 16 minus x squared, on the closed interval, -4, 4. Solution. The continuity on the closed interval, -4, 4, depends on the continuity on the open interval -4, 4, and the continuity at the endpoints x equals -4 and x equals 4. First, continuity on the open interval -4, 4. Show that the limit of f of x, as x approaches c, can be calculated by direct substitution of x equals c, for any c in -4, 4. Because the limit of f of x, as x approaches c, can be calculated by direct substitution of x equals c, for of any c in -4, 4, f is continuous on the open interval -4, 4. Second, continuity at the endpoints x equals -4 and x equals 4. Evaluate the limit from the right at x equals -4. Because the limit of f of x, as x approaches -4 from the right, can be calculated by direct substitution, f is continuous from the right of -4. Evaluate the limit from the left at x equals 4. Because the limit of f of x, as x approaches 4 from the left, can be calculated by direct substitution, f continuous from the left of 4. In conclusion, f is continuous on the open interval -4, 4, and continuous at endpoints x equal -4 and x equals 4. Therefore, f is continuous on the closed interval -4, 4. Number 2. f of x equals -x plus 4, if x is less than or equal to 1, and x plus 5 all over 2, if x is greater than 1, on the closed interval -2, 6. Solution: f is a piecewise function over a closed interval -2, 6. Its continuity depends on the continuity on the subintervals -2, 1 and 1, 6. the continuity at the transition point x equals 1. And the continuity at the endpoints x equals -2 and x equals 6. First, continuity on the subintervals and at the endpoints. f1 of x equals -+4 is a polynomial, which is continuous everywhere. Hence, f is continuous on the subinterval -2, 1, which includes the endpoint x equals -2. f2 of x equals x plus 5 all over 2 is a polynomial, which is also continuous everywhere. Thus, f is continuous on the subinterval 1, 6, which includes the endpoint x equals 6. Second, continuity at the transition point. At the transition point x equals 1, the equation for continuity at a point must be satisfied. The limit of f of x, as x approaches 1, equals f of 1, which entails the following conditions. A. Is f of 1 defined? Because x equals 1 is in the domain x less than or equal to 1 of f1 of x. f of 1 equals 3. Hence, f of 1 is defined. B. Does the limit of f of x, as x approaches 1, exist? The limit exists if the one-sided limits are equal. Because the one-sided limits are equal, the limit of f of x, as x approaches 1, exists, and it is equal to 3. C. Is the limit of f of x, as x approaches 1, equal to f of 1? They are both equal to 3. Hence, f is continuous at the transition point x equals 1. Third, continuity at the endpoints. This is an optional part since it has already been proven in the first part. At the endpoints x equal -2 and x equals 6, the equations must be satisfied. At x equals -2, the limit of -x plus 4, as x approaches negative from the right, is equal to 6. Hence, f of x is continuous from the right at a. At x equals 6. The limit of x plus 5 all over 2, as x approaches 6 from the left, is equal to 11 over 2. Thus, f of x is continuous from the left at b. Finally, because f is continuous on the subintervals -2, 1, and 1, 6, which include the endpoints x equals -2 and x equals 6, respectively. And f is continuous at the transition point x equals 1. It can be concluded that f is continuous on the closed interval (-2, 6). Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.